Okay, good morning, everybody. Can you hear me?
Yes, yes.
Yeah, we can hear
Okay.
you.
Yes,
Very
sir.
good morning.
A very warm welcome to everybody, and we've got a good participation today. And I see a lot of doctorate level people who are online today. So I'm shifting the presentation to maybe a little more technical. I'll be covering the basics as well as I'll be going into some in-depths because I see a lot of senior caliber people attending today. So I'll be tuning accordingly. Now, I'm Praveen Bell. I'm one of the directors and also the CTO of IndiaSoft Technologies. And I'm the handling automation studio for the last 10 years. And today, I think it's one of the only software in the world which is so evolved in hydraulics and pneumatics. So today's agenda, I'll just spell it out. Okay, just for information, Automation Studio applies to the subjects of hydraulics, pneumatics, proportional and hydraulics and pneumatics, industrial fluid power, mechatronics, PLC, automation, and a few other technologies. There are few interesting things I'm going to show you towards the end. We have a lot to see today. Okay. So as per the agenda, I will first give a brief introduction of Automation Studio. Then after that, how do we build circuits? What are the in-depth features of the various modules? There are more than 20 modules in Automation Studio. Then as far as educational circuits go, this is for curriculum-based circuits. I'll be showing you some of these and how beautifully you can conduct these lab practicals here. Then we'll be doing a fair bit of proportional and servo hydraulics because in the industry, uh, I could say around 60 to 70% of hydraulics is a servo and proportional hydraulics. And in this, we need to understand a lot of proportional devices, PID feedback control systems, etc. We'll be covering that. Then in the professional world, what happens in industrial fluid power? What are the type of work people are doing? Some defense cases I'll be covering. And I'm showing you all this because I see a lot of autonomous institutes which are there online today. And they are capable of adapting a lot of new subjects in the syllabus, which could be more industry oriented. Also, I'll be covering SFC. SFC is the, I would say, the more preferred language of programming PLCs today. Today, everybody is teaching ladder programming, but SFC is what is really used in the industry today. Then I'll be covering OPC as a communication standard today. OPC is today become the de facto standard for the automation industry, communication between software to software, software to PLCs, PLCs to SCADA devices, even to the IoT and cloud platforms. OPC has today become the backbone and it has a very strong relevance. So I'll be covering that today. And then in the end, some student projects which we've seen over the last few years and how to hardware interface the software to electro hydraulic pneumatic trainer kits. So now, if you see the screen, this is what automation today looks like. You will be seeing this in the working copy. So I'll not explain anything on this slide. As far as employability goes in the industry, these are the partial list of corporate users of Automation Studio. And you can see John Deere, Eaton, Komatsu, Caterpillar, a lot of automation companies also there. A lot cannot be listed out here because of non-disclosure agreements, because the user list is quite huge. And this is the user list. Now, I'll be covering just one or two slides, then we're shifting straight to the working copy. Now, this is what Automation Studio, the entire bundle contains. So if you see, this is the list of modules. So we have hydraulics and proportional hydraulics. Okay, so that is on-off type of hydraulics as well as PID feedback control system hydraulics. Then pneumatics and proportional pneumatics. We have more than 5,500 components today in Automation Studio. So that's a very big achievement. Then fluid power component sizing. This is specifically for design-based problems. A lot of colleges we've seen that they ignore the design aspect of industrial fluid power. And in the laboratory practicals, it is written that do a design-based experiment. But connecting 4 or 5 components and them working in a particular sequence is not design. A design is maybe a piston carrying a load of 1 ton at an angle of 30 degrees should extract in exactly 4.5 seconds. How do I do a calculation like that? That is known as design based. And that is what this fluid power component sizing module helps you to do. Then we have mechanisms and mechanical linkages. This creates mechanisms and simulates real life loading conditions. For example, a piston pushing a cantilever arm, or it could be a linkage chain, 4 or 5 pivots working on a excavator arm. How does this loading happen and how does this entire mechanism behave? This is module is there. Then we have troubleshooting, diagnostics, bill of materials. Then the red section is the entire control section. So if you see, we have electrical controls, JIC, IEC, push buttons, solenoids, contactors, relays to create electro-hydraulic, electro-pneumatic trainer kits. Electro-pneumatic circuits. Then in ladder logic, we have 4 types of ladder logics. We have Allen Bradley, Siemens, IEC, and LSys. You can build ladder diagrams on the same screen and operate hydraulic pneumatic circuits. Then we also have SFC and GraphSet. This is the alternative programming language for PLCs today. Now, whenever you buy a PLC in the market today, it supports multiple programming languages. That is, one is the ladder logic, the traditional method. Then you have functional block diagrams, you have instruction loops, and then there is SFC. So SFC in the industry has got the biggest market share of PLC programming. So it has become important. Then digital electronics, this is not a full-fledged analog or a digital electronic software, but components such as AND gates, OR gates, SRJK, D flip-flops, verification of De Morgan's theorems, these things you can do in this particular module. So I think the practicals for first, second year, these common electronic practicals can be done in this. And these circuits can also be connected to your hydraulic pneumatic circuits. Then coming to people who want to do advanced level of work, we have a mathematical block diagram library. There are certain few people in the country uh, who do a lot of control system design for industrial fluid power, and they use software like Simulink, LabVIEW, etc. for the control section bit. But now Automation Studio themselves have incorporated a block diagram library inside Automation Studio. So you don't have to resort to API co-simulation between two software or communication between two software. You can build the entire block diagram control system inside Automation Studio. Then we have HMI control panels. You can build all type of HMI panels. We also have 2D and 3D animations and virtual machines. Then we also have a hardware interface. So 1 minute view. Okay. Now in the latest version 7.1, there have been a lot of improvements. So in the last 8 years, Automation Studio, I'll tell you about the versions. There was 5.6, 5.7, there was 6.0, 6.1, 6.2, 6.3, 6.4, 7, and now we are sitting on version 7.1. So every 6 months or 1 year, there is either a big upgrade or there is a new release. And it is improving leaps and bounds. So one of the good features in the current version is we've got illustrated libraries. So these libraries, for example, if you see this, these are libraries for PLCs. So around 40 to 50 of PLCs, how they actually look in real life, and the wiring, because rarely a student gets to know how a PLC is wired externally. So this PLC wiring can be done. Then also in hydraulics, pneumatics, there are a lot of cross-section and illustrated components available now. This is mainly for didactic and teaching purposes. Obviously, there are a lot of technical improvements. Then we also have an interface kit. So with Automation Studio, you can directly create a PLC or an electrical control circuit and directly online link it to an electro-hydraulic, electro-pneumatic kit. So this is a brief. And today in India, we have more than, I think, 200-300 colleges right from NIT Meghalaya, IIT Guwahati, Anna University, a lot of people, and they're already users. So this is what Automation Studio looks like. Okay. So on the left, we have this entire list of libraries, more than 5,000 components. But before we go there, let me take you to the simulation power of Automation Studio as a simulation engine. This is specifically for people who are into simulation. So if you see, we have a simulation pace right up to 1 microsecond today. So around 4 years back, we were at 10 milliseconds. Now it's come down to around 1 microsecond. Up to that sampling rate we can do. Then we have things like acceleration of gravity, because this is very important, because if a piston is horizontal and in movement, of changing its angle. The loading conditions and the pressure buildups are very different. This is a very important factor for online dynamic simulation. Then we have things like cavitation simulation, that is the air percentage and the fluids. What happens to that? Then we have things like perfect reliance. We can do thermal simulation of these 2D circuits. A lot of features in the background. Then also, if you come to the fluid section, we have a fluid and line manager. Now, this is again very powerful. Before building any circuit, you can select the type of fluid you want to use. And the fluid has its bulk modulus values, the bulk pressures, densities, kinematic viscosities, at what temperature, what is the viscosity graphs, etc. These are all hundreds of fluids available in the market. Obviously, you can create your own fluid also from scratch if you know the properties. Then till a few years back, pneumatics was only considered as air. But today we have things like butane, carbon dioxide, helium, hydrogen, propane, different types of gases. Their compressibility factors, they are taken into account. So this is there. Then in materials, we have different types of materials, stainless steel, rusted, cast iron, internal roughness of pipes. These are taken into consideration. So all these are there in the background. This to give you a brief because you have to understand why it is a good simulation software. Now, building of circuits is very easy. I will not be wasting too much time building things. Just one basic circuit I'll build online. The rest, I've kept everything ready so we can see all the features. So I'll pull out some components. Okay. And I'll just join these. I can zoom. Yeah. So it's all a drag and drop, easy to use interface. Training does not require more than 1 or 2 days. It is that easier software to use. So I connect all these red dots and in a matter of seconds, I build a simple piston extraction circuit. Now, before simulating this, let's see the component properties. If you go to the pump, we have different types of pump configurations. We have a what you call as a head loss curve based pump. We have an ideal pump. We have rotodynamic curve pumps. For example, let's say if I take a performance curve pump and I come to the performance curves, you can see these are the curves. So these are the curves which match the technical specifications by when you buy a pump from the market. It has this head loss curves defined. So you can make this pump behave like the real pump which you bought out. So that mapping is possible. If you come to the valve, you can see that I have this particular configuration. This valve is totally configurable in the sense that if I want to change a particular spool, I have hundreds of spools available here. Okay, I can choose the type of spool I want. Let's say I want to make a 7x3 wall. You'll see that only 7x3 spools will appear here. So I can configure a wall totally from scratch. Now, for advanced users who really work at this level, you can see that this wall allows you to have access to the internal flow curves. A lot of people in the industry, defense organizations, people are doing critical equipment. We are working with a lot of defense organizations who are building projects in automation studio, and they need access to the internal flow curves, how this wall behaves, because these applications are very, very critical. So you can set these port to port. Okay. Then the internal pressure drop curves, they can be set. Then the internal leakage, all this can be done. So totally configurable walls. Then obviously the other parameters are there. You can also do things like if I don't want a spring, I can change it into a push button or any type of a valve operator. So this valve is totally configurable. If I come to the piston, similarly, the piston is also totally configurable. So is it at an angle? What is the inclination? Okay. All these is configurable. 1 minute. Yeah. Then things like, do you want to put a damping spring on one side, the other side? The moment I insert a spring, it will show me the K spring stiffness value. It will ask me for things like that. So these are also totally configurable. I can put the force curves also, opposing forces, driving forces, etc. So that is what I'm trying to say. These are totally customizable and a lot of in-depth parameters available. Now for simulation, I click on the simulation button and I operate the lever. And you can see that this thing is moving. And while simulation is going on, I can maybe go and change the displacement of my pump. You can see the piston moves faster. I can change the cracking pressure of my pressure relief valve. I can see the immediate effects on my particular circuit. Now, what is more important is I need to measure values. I need to take plots, graphs. That is more important, because one thing is for sure, Automation Studio can build almost every possible hydraulic pneumatic circuit. You can pick up any textbook. The typical textbook used is Anthony Esposito for industrial fluid power. We've seen it being used in India and worldwide. So even in Anthony Esposito, if you see chapter number 18 today is a chapter on Automation Studio. So they have a direct tie-up, Anthony Esposito and Farming Technologies. So chapter number 18 is Automation Studio. So circuits are possible. Only thing is, how do we simulate and how do we make our lab practicals much superior and better? So now in simulation, we have these dynamic measuring instruments. For example, if I click on a component and a drag, it has automatically detected that for this particular component, I can measure linear position, speed, etc. Only those values for that particular component. Okay. Then if I click on a node, at this particular node, I can measure pressure, density, temperature, viscosity. Or if I say between two nodes, let's say between this point and this particular port, it automatically detects differential pressure. So a lot of this has happened automatically. I simulate this and you can see the values appearing on my measuring instruments. Now these are dynamic measuring instruments. Obviously, I can put all my pressure gauges, etc., flow meters, which are available in the library. But these dynamic measuring instruments are like probes. You can point at any point in the circuit and measure a particular value. Even MATLAB Simulink has a floating oscilloscope concept. I put it on the screen, point at any point, it measures a value there. So this concept is very similar. Now, besides that, we have a very powerful plotter module in Automation Studio. So at a time, we can open up four types of four plotters. Two plotters are time-based plotters. Okay. Then the third plotter is two parameters versus each other, y versus x. And the fourth plotter is z, y, x, three parameters versus each other. So at a time, I can use four plotters. Right now, we'll take one. I drag a component and put it on the plotter screen. It automatically detects that I can measure these values. So I say linear position. I say OK. And for the pump, I say I want to measure the, let's say the output flow Q. And I simulate this particular circuit. Okay. And immediately I can see my waveforms here. So now this plotter is very flexible. For example, I can hold this axis and move it up and down. Okay. This is possible. Then I can zoom into any area. I can also put these marker points because these are important to take measurements. So when I put two marker points here, it shows me delta T is equal to 0.5 seconds. So this is the time of extraction of that particular piston. I can also right click and I can say copy this plotter image. It will create an image and I can paste it in my Microsoft PowerPoint presentation, Microsoft Word if you're creating a project report, etc. I can also export these measurements. So it will export a table in an Excel type of a format if you want to take it for further analysis to any other software. So these values can also be exported. So these are the features. A few components also have cross-section animations. We also have an entire different library for cross-section animations. Okay, this is also available. Obviously, every component you can right click and you can go to the help and there'll be lots of help available, every component. So this was the basic way of building a circuit. And now what we'll do is we'll open up circuits and I'll show them to you, which are made in a kept ready for you. And it will explore new features in every circuit which I show you. So we'll go progressively with better and better features. I know you'll have a lot of questions, but I'm sure that almost all of them will be answered by the time we end this particular demonstration. So, okay. Now starting at the basics, we start teaching industrial fluid power with things like ISO symbols. So in Automation Studio, you see at the bottom left, we have ISO 1219, 91, and we have 2012. So both these are available. You can see here the differences in the symbols, how they look, how they have been modified in the different ISO standards here. So you can start with this. This is just more of a CAD, what do you say, CAD study. That this is what the symbols are, how they were in the previous ISO and how they look today. Okay, so these are there. So you can build a study experiment in this. Then coming to one. Wrong folder, sorry, here. That is there. Then there is things like, let's say, fluid properties. Now, we also teach students fluid properties. You may or may not teach, but what I'm trying to expose here is that we teach these subjects, but students really don't get to see the effect on a particular circuit. So here there are two circuits which are similar, only the fluids used are little different. So the temperatures are the same, but in the left-hand side, we've used non-polished steel. In the right, there is something else. And when we simulate these two circuits together, you can actually see the difference on the piston extraction times because the materials and fluids used are actually different in both the cases. So they do have an effect on the circuit at a micro level. So fluid properties can be studied. Then we also teach students study of linear and rotary actuators. Okay. But in Automation Studio, you can actually create a valid experiment as to what type of experiment do I want to do on a linear actuator. We have trainer kits, but they are very limited. You cannot size them. You cannot change a lot of things. The amount of experiments are limited. You cannot take graphs. You cannot take plots. A lot of things are not possible on hardware trainer kits. So in Automation Studio, we have an entire list of hundreds of different types of linear actuators, telescopic, mechanically linked, double rod, single rod, a huge list of cylinders are there, linear actuators. And we can actually create an experiment in Automation Studio. Now here, if you see these two circuits here in the center, if you see they're exactly the same circuits, only in the first case, the piston is horizontal. In the second case, it is vertical. The load carrying capacity is the same. Okay. So when the piston is horizontal, it is able to extract a load of 6.7 tons here. Okay. Whereas the moment it shifts to vertical, it is not able to pick up this particular load because of the effect of gravity. So in this case, we can do a lot of things. Either we change the diameter of the particular piston, but in this case, what I'll do is I'll change the cracking pressure. Yeah. From 80 bar, I shifted to 112 bar and it was able to overcome that particular load. I reduce it, it buckles again. So in this way, I can create valid experiments. Okay. Now, even in this case, yeah. Piston extraction time at 100 bar cracking pressure and 80 bar cracking pressure. What are the times of piston extraction? All these can be measured. So these become valid experiments rather than just study experiments. You can actually take down readings, etc. Similarly, we also have rotary actuators. We'll skip that because we have too much of content today. Then coming to pneumatics, we usually start pneumatics with things like air preparation. We have filters, we have coolers, we have these type of devices. So here all these are available. Okay, FRL, filters, regulators, and these can be modeled. And you can connect them to pneumatic lines. You can see the pressure drops. So these are possible. Okay. And these are further used in certain things like what is known as air distribution systems. Now, a lot of teachers a few years back came to me asking, how do we design an air distribution system? Because it is there in our practical and we don't know what to do about this. Now, the funny thing is that this air distribution system is not there in Anthony Esposito. It is there in Mujumdar textbook in pneumatics. So in air distribution system, there are certain criteria. Now, there are different types of air distribution system. For example, there is something known as a conventional network. There's an octopus network. There's a closed loop network. The closed loop is supposed to be the most efficient because of the air routing. Also, you'll find in the same textbook, there are certain conditions to be met, that the pressure drop on the main line should not be more than 0.03 bar. Then between the start and the end point, the pressure drop should not be more than 1 bar. There are certain conditions which have to be met. So we can go around and build the entire closed loop system like this. This is a pneumatic air distribution system. So if I simulate this, you can see that on the main line, my pressure drop, sorry, from the first point to the end point is 0.072 bar here. Okay, this is maintained. Then I can check the pressure drops at all points across the fittings also, elbow fittings, T fittings, etc. Then if you see at a point like this, the air is coming from both sides. That is because the air requirement here is higher than the rest of the closed loop circuit. So such type of circuits are almost impossible to design by hand or do mathematical calculation. So this actually helps you to create and visualize. You can play around with the diameters of the pipes, etc. Very simple things. For example, let's say we take only the line, one single line segment here. This is a 150 meter line, 15 mm thickness. If I simulate this, you can see the pressure drop on this line is 0.258 bar, and this is not acceptable for a optimized air distribution system. We cannot work with such a high pressure drop. So we go here, we go to the line, and we say make this 15 mm into 25 mm. I say okay. Assimilate, and now you see the pressure drop is now reduced to 0.02 bar. This is acceptable for a air distribution system. So such things you can play around and build your circuits. So that was a air distribution system. Then coming to illustrated hydraulics, I told you that in the new versions they've introduced a special library for components which are illustrated. Okay, and they look something like this. Yeah, these are mainly for teaching purposes. Okay, yeah, and these can be simulated. So these, yeah, extend, retract. So these are illustrated libraries. So now this is a new thing, specially targeted at teaching purposes. So teachers in the classroom can actually show this behavior, not as a YouTube animation video, but as an actual simulated animation. So there's an entire library for these illustrated components for hydraulics, pneumatics, electrical components, as well as PLCs also. So these are now available. Okay. That was illustrated. Where is gone? Yeah, that was illustrated. Then coming to electro hydraulics and electro pneumatics. Automation Studio has two types of electrical control libraries, IC and JIC. So depending on what textbook you follow, because those components look quite different when you're using different types of electrical standards. Now, for example, I'll just give a small example. In JIC, a solenoid valve looks something like this. Okay, something like this. But the same solenoid, if you go to IC, it looks very different like this. Okay, so one is European, one is American. So depending on what textbook you use, both are available for creating circuits, and it will avoid the confusion whether this component is supposed to be used or this one. Because a lot of times I've seen mixed type of terminology being used in these diagrams. It becomes confusing. So in this case, we have a piston, and on this piston there are two sensors put. One is when the piston is at 0 position, there's a sensor 1, and when the piston fully extracts, there is a sensor 2 here. Okay. Now these sensors give signal to these two electrical switches on the electrical circuit here. And the solenoids coils are actually the coils belonging to the valve here. Okay. And there's a HMI panel at the top here. We have a HMI library, like I told you. You can build fancy looking HMI panels. If I simulate the circuit, now because of the way the circuit is built, you can see how these sensors are getting triggered. You can see these sensor switches on the electrical circuit. They are opening and closing. Okay. And this circuit is operating. And being a fluid power background, we can see that it will plot these curves. You can even do things like if I reduce the pump displacement, the entire circuit will automatically slow down in response to the electrical signals receiving. So basically, it is a actual dynamic simulation with a very powerful engine working in the background. I increase the pump displacement, entire circuit speeds up here. So all these things you can do. This is an electro hydraulic circuit. You can build any type of electro hydraulic circuit you want. A lot of students have done projects where there are 5 pistons working in a particular batching process. One operates, then the second, then the third in a particular sequence. All that is possible. Now coming to a very common practical in educational, that is we teach students metering circuits. Okay. Again, I've seen a lot of confusion as to the explanation of metering circuits, what they mean, and how do I actually do a practical on this. So meter in means fluid coming into an actuator. So if you see this here, this flow line, you can see this valve here, orifice valve. Fluid is coming into the actuator from the left hand side. So this is known as a meter in, coming from the piston side. At the same time, if you see this circuit on the right, this is also a meter in circuit. Because in the left hand side, fluid is entering from the piston side in this direction. And in the reverse direction, fluid is also entering the cylinder from the rod side. So both these are considered as a meter in concept. Okay. And if I simulate this, piston goes slowly in the forward direction, whereas in the reverse direction, the non-return valve opens up and it comes back fast. Okay. And these curves can be plotted. You can actually measure the piston extraction times in forward and reverse direction. Similarly, in meter in, with metering on both sides, you can play around with these valve openings here. And then decide the speed control both in forward as well as in reverse direction. Okay. Now in meter out, meter out means flow is coming from the left hand side, but it is coming out from the rod side. And that is what we are controlling here using this orifice valve. So fluid coming out of the actuator is known as meter out. And this also is a meter out circuit. Fluid coming out from reverse direction and forward direction. This, if we simulate again, this can again become speed control. So a simple experiment of meter in, meter out speed control of hydraulic pneumatic circuits can be done in a very beautiful fashion. And why? Because we can take these plots and we have valid readings. Yeah. So same thing can be done in a much more powerful visual way. So that was metering circuits. Then coming to something more technical, which typically is not taught in educational, but very valid for corporate industry, is when you're building a circuit, how are you applying the load and loading conditions on your particular circuits? Okay. And these are very important. So otherwise, we don't know how that entire circuit is going to behave. What is the pressure buildup? Will a particular hose burst? Okay, what do I need to do to improve the circuit, etc., etc. So now let's take an example of a bulldozer, and there's a piston mounted on the bulldozer. It's a very simplified circuit. Real life circuits are very complex. This is a very, very simplified circuit. And I want to tell this piston rod that I'm facing opposing force as the piston is moving. This bulldozer is pushing sand. Sand is piling up. So the opposing force is going to change. Okay. And for that, I have this force curves, resistive force curves here. I can set the opposing force for this piston moving from 0 to 100% here. I can set this. So I've set an approximate force F, opposing force. And then in my plotter, I'm measuring the pressure buildup. So I simulate the circuit. I start the simulation. Okay. And I have paused the simulation because there is something very interesting to see. Now, this is interesting to know. If you see, the piston has stopped at around 80% of piston extraction stroke here. Okay. At that very point, there's a spike in the system. This blue graph, if you see, this blue graph, there's a spike in the system here. Okay. Because the opposing force was so high that it could not push anymore. It came to a stop force here. Now, you as an engineer, what do you want to do? How do you overcome this situation? There are many options you can try. One is increase the diameter of the cylinder. Second is you can increase the cracking pressure. You can try increasing the pump flow, or you can even do things like put an accumulator in the circuit. There are different ways of addressing this problem. So that is what actually an engineer does in the industry. How do I address this problem? So in this case, let's say I just change the cracking pressure. I made it to 120 bar, still not sufficient. Now around 230 bar, it has extended. Okay. Now 230 is a very high pressure, not actually feasible in the industry. But yeah, this is a way of doing this problem. There are other ways. You can increase the diameter of the particular cylinder. That is the easier way to do it. So how do you solve these problems? So these are loading conditions. You have driving force as well as you have resistive force curves. Now, this very simple circuit from Anthony Esposito textbook is that of a hydraulic jack. When a car gets punctured, you put it under the car, and with a handle, you're pumping hydraulic fluid. So there's no pump, there is no electrical power supply. Okay, there's a piston on the left which you're driving with your hand. And for that, we have this driving force curve here, positive and negative driving force. It's like holding the rod of the uh, piston and moving it up and down. And so if I simulate this, the left-hand side piston moves on its own because I am driving it with my hands. It is pulling out fluid and sending it to the lifting cylinder here. Okay. So such type of interesting practicals, you can see them in motion. Okay. Then coming to a very interesting section, that is sizing of cylinder, sizing sheet calculator. This is specifically for design-based calculations. IIT ISM Dhanbad is a user of Automation Studio, IIT Guwahati, NIT Meghalaya. Anna University, there are a lot of people, and in certain pockets, people are doing design-based studies, and design-based calculations are very important for people who are mainly at a higher UG level or maybe PG and research level, system research. Now, in this particular system, the aim is that I want to extract this piston from 0 to 100% in exactly maybe 2.5 seconds, 3 seconds. So how do I go around doing this calculation without having to calculate manually? Okay. So Automation Studio has a sizing sheet module available with it. So we have a pump here. This pump is pumping at 120 liters per minute, 1000 cubic centimeters per revolution, 1200 RPM. That is the rating of this pump. So if I double click on this pump, I go to the data and I note down the Q, that is the output flow. Where has it gone? Yeah, rated flow. Rated flow QR 120 liters per minute. I note this down because that is the flow coming to my cylinder here. Okay. Now double click on the cylinder, and in my cylinder, I have this sizing sheet manager. What happened? 1 minute, something has gone wrong. Let me just reinsert the cylinder. for this project. Okay, I'll just start a new project. Something has locked the properties of this project one. Give me a few seconds, I'll just build this. Because this is an important section of Automation Studio. Sizing sheet, why is it stopped here? Okay, something seems to be a problem. I'll just sort this later on. We'll move on with this demo. 1 minute. Let me see if it is there in another circuit. Okay, something has locked my sizing sheet. I don't know why. I'll try to sort this later on. So we'll skip sizing sheet as of now. This was working yesterday. 1 minute. Automation Studio demo 7.1 sizing. No, something has locked it. I'll figure this later on. We'll continue with the demo. I'll show you sizing sheet later on. So sizing, something has happened. Okay. Okay, coming to troubleshooting, Automation Studio has a very interesting troubleshooting options available in Automation Studio. Now, no machinery in the world can automatically troubleshoot. There'll be a troubleshooting procedure. Let it be a Komatsu mining machine or let it be something else. They'll have a procedure for troubleshooting. That if this is not happening, there's a sequence to follow. So you can build troubleshooting procedures in Automation Studio. For example, if you see the components here, you have this cylinder. We have a troubleshooting option here. And here you can declare faults. For example, you can jam a particular piston, high damping coefficient. Okay, there are different, troubleshooting options available here. So this is for a piston. If you see a pressure relief valve, it has different types of faults here. Faulty opening, cannot reseat properly, cannot open, always fully open, different types of faults. Not only that, you can also trigger the fault for a particular condition. That I want this faulty opening to get triggered when maximum pressure has been reached. So conditions for failure, those can also be defined. So now how can you make an interesting practical for students and a troubleshooting procedure? Now in this particular circuit, if you see, this piston extraction is happening fine, not a problem at all. Then I come to this piston. I go to the troubleshooting option. I say jam the particular piston, activate the failure, and I say okay. Okay. Now if I simulate, you can see that this piston is not extracting because it is jammed. Yes. Yeah, someone has raised a hand.
Yeah. Sir, can I ask
What
something,
is the
sir?
query?
Yeah, sir, my query was that cracking
Someone
pressure,
has
suppose.
raised. No, I can't hear.
1 minute.
You'll have to unmute him maybe.
1 minute.
Can anyone hear me? Can you hear me, sir?
Yes, 1 minute.
Yes, sir. Hello.
Hello.
Yes, sir.
Yeah, can I ask my question?
Yes, sir.
Just can you just open the like the circuit? In that circuit only, I will try to.
Okay,
This
this one.
Yeah, that circuit that you opened, no? Yeah. Sir, I think your voice is reverberating, sir. Actually.
There's a feedback here. One minute.
Okay,
Just disable this. Let me. One minute. I'll just. Yes, sir, you can talk to me. My speakers
Sir,
also. Yes.
okay, okay. So my question was, suppose I have set a
Yes,
pressure
sir.
relief. Hello.
Hello.
Yeah, yeah, sir. I'm asking my question. Suppose this pressure relief valve, I have set a.
One minute, sir. 1 minute, sir. Just
Yeah, put on my one minute. Correct. I'm on the this monitor. No, 1 minute. I'll just shift the speaker. Just hold on, sir. 1 minute.
Okay, okay.
Speaker will be shifted to. Okay. Hello.
Hello.
Yeah. Yeah. Now I can hear.
Yeah, yeah, sir. If you open the circuit, sir, once.
Hmm. Yes, sir.
Yeah. Suppose, sir, I have set one pressure, okay, here, which is higher than the, suppose the pressure which will be, which the piston will be facing while removing the load, 15% more than that, like obviously it will have to, it will be under some pressure. So here the pressure will be set at 15% higher than what it will be facing here. Okay. So like this load by area. So then suppose the pressure is 80 bar. Here I have set the pressure at 80 bar. Okay. So
Let's say you are looking at 80 bar. Okay.
okay. Yeah. Suppose I have set the pressure here at 80 bar or 70 bar, whatever, sir. Just hello.
Yeah, I can hear you.
Yeah. Suppose that this is cracking pressure. So when the fluid pressure in the hydraulic circuit, when it will try to cross 80 bar, then this one spool will move up, and all the, if it is completely open from normally closed position to normally open position, when it will be coming to that time, the entire flow will be directed to the tank from the pump, right? So
Correct.
so that time in this line, no, which is from the pump outlet to the hydraulic cylinder, in this line, sir, I am talking about.
Yeah.
Yeah, in this line, the
This
pressure
line.
will be at, the pressure will be at 80 bar only, no, it will be static, right, that time.
No, 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 no. It doesn't work like that. I'll tell you. I'll tell you how it works.
Okay.
See, what happens is
Yeah, yeah.
the system pressure is at 80 bar. That is decided by the pressure relief valve. Okay. Now, what happens is this piston rod does not have any opposing force as of now.
Okay.
Okay. So now what I'm plotting in the plotter is the pressure in the cylinder on the piston side. Okay. Now, if you see, I'll explain the behavior. Okay.
Okay.
1 minute. I've jammed this piston. Let me just unjam it. I'm trying to show you something else. 1 minute. Yeah. I'll explain this exactly how this happens.
No, sir, what I wanted to make sure is, like,
See, I'll explain this. This is in the graph. It will be very clear now. I'll tell you why this is the pressure. Okay. Now, if you see, when I activated the valve, if you see at the bottom here, the pressure up to 1 point was 0. Because this piston is free, there's no opposing force, there's nothing acting on it. So there's a 0 bar pressure at the piston side of the cylinder.
Yeah.
Now, the moment the piston hits the end position, that is the wall of the cylinder, it is come to a stop position.
Yeah.
That is full force stop. And that
Yeah.
time, the full force, the pressure of 80 bars, if you see in the graph here, you see 80 bar here. It has come to 80 bar. There's a spike when it hits the wall of the particular cylinder.
Yeah.
And that is the time the cylinder can't move, and the full 80 bars from the pump is hitting the piston disc.
Yeah. And sir,
And that is when
actually,
the pressure relief valve trips, and that's when it starts of outletting the extra pressure there.
Okay, sir. The same thing actually I was trying to convey. Say,
Hmm.
yeah, when there is no load, so when the piston is moving, say, from A to B, from one end to another end, that time
Hmm.
definitely we can't see any load here, so it will be moving freely. So that's why it is at zero pressure. So
Yeah.
once it gets to the other end, that
Hmm.
time like pump is still actually pumping the
Pumping
fluid, right? So that's
through
why
pressure relief valve.
yeah, yeah, like
Yeah.
at the end when it reaches that time still actually the pump is pumping the fluid, so that's
Yes.
why eventually the pressure increases, and at 80 bar, when it reaches 80 bar, as I said the relief valve at 80 bar, that time the relief valve opens and the entire pump flow uh, uh, gets discharged to the tank, right? So
Yes.
that so that as we can see the pressure from the graph, actually from the graph, just 1 second sir, give me some. Yeah, at the here we can see the as the piston hits the other end while moving, so as it hits the other end, and as the fluid is actually getting discharged to the tank, that time in the system, in the hydraulic actuator, the pressure is then we have achieved 80 bar. That's correct, right?
Correct.
Yeah, so that was actually one of my questions. And
See, that
another
is the
question.
one thing. I'll show you certain more interesting things, sir. Now, since you brought this up, I just tell you now. Suppose I go to force curves now, resistive force curve. Okay.
Okay.
Now, during extraction, okay, let's say I put a opposing force here like this. Okay. So
Yeah.
now the piston is not totally free. As it is moving, there's going to be opposing force. Now
Yeah.
here, if I simulate this, you'll see pressure starts rising even in between. See here?
Yeah. Yeah. Yeah.
Okay. So
Hmm.
this is one condition. Another interesting condition I'll show you, which since you brought up this particular topic, it's interesting to know the behavior.
Uh, Sir,
Now I put
another
a,
one problem what I was facing is, sir. Uh,
so 1 minute, let me just show this, then you can, if
okay. Okay.
because this
Okay.
is interesting, I just want to show you something.
Okay. Okay. Sure. Sir.
Now I put this cylinder inside, I say linear position, okay. But what I do is I set my cracking pressure to 0 and I operate my piston.
Hmm.
You see in a condition like this, there is still movement in the piston. Now
Yes.
this is a real life behavior because the pressure relief valve trips only when there is flow in this entire line. It hits the piston disc and there's a back pressure which comes and trips the pressure relief valve.
Hmm.
So even at a rating of around 0 bar, there will be slight movement here.
So
Get
in
me?
yeah, yeah, sir, I got it, sir. So
Yeah.
in one of the simulations, sir.
Yeah.
Uh, so, sir, actually, once this session ends,
Yeah.
can you can I have 1 or 2 minutes? I wanted
Yes,
to
yes,
discuss
definitely,
one
sir.
system.
So we have a
So
lot
yeah,
to show. We'll have a QA in the end.
okay,
Or we
okay.
can
So,
personally
sir,
connect also, not a problem.
okay, sir. Thank you for that, sir.
Because a
So,
lot of things to show, we are running out of time. We'll sit,
so
don't worry, there are a lot of interesting. We'll sit, we'll discuss, we'll have a separate session with you, no problem, sir.
okay, okay. So, sir, actually, let me conclude what I was trying to say. So,
Huh,
when the cracking pressure is reached and the entire
huh.
pump flow gets discharged to the tank, that time in in the cylinder also we have achieved say 90 bar. Here also 90 bar. The setup here is 90 bar. The setting is 90
Yes,
bar. So when it gets to the other end, I mean, when the entire flow is getting discharged here, that time in the cylinder hydraulic actuator also the pressure that the piston is like facing, that is also 90 watt. That's it, right, sir?
yes,
Okay, sir.
yeah.
So, sir, once the session gets end, please, like I request you for 5 minutes discussion.
Yes, yes,
So,
definitely, sir. No, don't worry.
Yeah. So
No
I have
problem.
like made one presentation also so that I can convey what I wanted to ask.
Yes, yes, no problem.
Okay. Okay. Thank you, sir.
So we were trying to show troubleshooting. So in this case, what we are doing is on this piston, we are jamming this particular piston and we are activating the failure. And now it cannot operate. So now we have a hydraulic tester here. This is the type of tester the engineers use on the field. And we connect this to these two ports here. The moment I connected this tester, you can see there's flow through this particular tester, which means that this entire circuit up to these 2 points is perfectly fine. There is some problem in this particular cylinder here. Okay. So I switch off the tester. Then I take a repair tool. I click on the cylinder. I say select the failure and repair it. Now it works fine. So such type of simple troubleshooting experience we can do. So we have thermometer, we have pressure gauge, we have hydraulic tester, repair and failure tool. So this is for troubleshooting. Then coming to college circuits, there are a lot of circuits. I really don't know how to, we can't cover all of them, but just one small circuit of an accumulator to show how well you can do a college practical. Let's say practical of study of accumulators. So Automation Studio has an entire list of accumulators available, gas loaded, spring loaded, etc. So these two circuits are exactly the same circuits, same design. Only the one on the left does not have an accumulator, and on the one right there is an accumulator. So accumulator we know acts as an extra power source, etc. So now if I simulate the circuit on my left, piston extracts, the accumulator has charged. If I operate the other circuit, you can see in the graph that the one without the accumulator took a lot of time to extract, whereas the one with the accumulator, the rise time was very fast. So this becomes a valid experiment. You can actually measure piston extraction times based on the accumulator sizing. So that was accumulator, then a regenerative circuit, etc., etc. A lot of them are there. Now, mechanism manager. Now, this is for, again for people who are doing senior level of work who want to do sort of real life loading conditions. So, what are mechanisms? See, mechanisms particularly come in handy. People who are doing corporate projects, and all these conditions have to be defined and taken into consideration while doing your design calculation. For example, we have this sort of a crane here on which there are two pistons mounted. So, the hydraulic is only one part of it, but this piston is at an angle, or while the crane is extracting a particular arm, the piston inclination is also changing. It may be fluctuating between 30 to 45 degrees. Also, the particular arm has got a particular it's got a center of mass. There are a lot of mechanical properties associated with this particular mechanism. Also in the textbook, Anthony Esposito, if you see, these are scans from that particular textbook, which is used across the world and in India. These are the type of mechanism defined that the piston is actually doing this type of work. There are loads, okay, cantilever arms, different types of pivot joints, linkages, etc. And in the industry, if it is, let's say, example, an excavator arm like this, then how is this mechanism behaving? So these are very, very important when you're doing design-based calculations and real-life loading conditions. So for example, in this, the piston is extracting, but in the physical world, this piston is operating a cantilever arm, and that cantilever arm has a load on the extreme end of it. So this is the cylinder operating a pivot arm, and that particular mechanism is defined in this particular mechanism manager here. This is the mechanism manager. There's a way to build this. We cannot do it in today's session, how to build this, but anyone interested, we can take a separate session. Now, if I simulate this particular circuit, you can see the mechanism behaving. I'm operating the valve, and here you can see the mechanism behaving. So this is actually simulating the real loading conditions. At the extreme end, there's a force in the minus Z direction and a cantilever arm. So different types of mechanisms. You can create an automation studio. Also in version 7.0, they have introduced a rotary mechanism. So if there is a rotary shaft and it is operating another type of a circuit, for example, in this case, such a type of a mechanism, a flywheel is actually driving a piston here. So such type of mechanisms, these can be done. These come in very handy for projects, real life conditions. Then coming to industry, let's say a lot of industries using the software Eaton, Bosch Rexroth, Myco. Now these are circuits from, this is a braking circuit of a Myco manifold block. The braking circuit. So typically what students do, we've seen they go to Google, they'll go to a corporate company like Eaton, Bosch, Myco, etc. And we can take a test bed circuit from them, like this braking system, and then they can simulate the entire thing with their design conditions. It becomes a project by itself. So this is an industry-based circuit from Myco. Then let's say Eaton priority valve. Now, what we teach in colleges and what is available in the industry, there are a lot of different things available in the industry. Now, for example, Eaton manufactures this manifold block, this entire light blue block, and a priority valve. A priority valve is a valve which, when operated, diverts the fluid on priority to a particular section. So, in this case, yeah, the moment I operate the power steering, the lifting mechanism of the bulldozer stops and the fluid is diverted on priority to the steering block. If I leave the steering block and I stop operating it, you'll see the lifting mechanism will start operating here. The moment I operate the steering wheel, the lifting mechanism stops and steering operates. So such type of manifold blocks and applications are there in the industry. And they're very typical. For example, there is something known as PVG, proportional valve groups, then Eaton system stack valves. These are all used in the industry. They are nothing like what we see in textbooks. I'll be showing you some of those. So that was the basic hydraulics. Now coming to proportional hydraulics. Yeah. I'm trying to fit in as much as I can. Can you see the video on your screen? No? Okay. Now, proportional hydraulics is where you control movements of actuators by using things like joysticks, steering wheels, feedback devices, etc. You actually go into this is a video of a Caterpillar excavator. So if you see inside the control cabin, there are foot pedals, there are joysticks, multiple types of devices available. And these are used for controlling this equipment. Okay. So now in proportional hydraulics, the components available are very different. You will have different types of valves, you'll have joysticks, you'll have PID controllers, circuits, etc. And in the proportional area, there are basically two types of valves available. One is proportional and one is known as servo valves. Okay. Proportional are what is a solenoid operated, which can accept an analog signal. Servo valves have a motor mounted on top of the valve. So if you see the images, if you see this solenoid valve here, this is a proportional valve here. And the symbol is at the bottom here, it has got an arrow on the solenoid, which means that it can accept an analog signal. Whereas the servo valve, there's a motor mounted, and you see the symbol. You see the symbol of a round circle here, which indicates a motor feedback. And what differentiates this valves is the flow curves. Okay. Whenever a valve is opening, it has an internal flow curve. So if you see at zero position, there is no flow. But as the spool starts opening up, there is a dead band in the middle. So if this dead band is 3% or more, it comes in a proportional valve category. Whereas if this dead band is around 1% or less, it comes into servo valve category. And that is what differentiates servo and proportional valves. We don't have time to see these videos. We'll see the circuit building of these. This is how a servo valve looks, a motor mounted on top. Whereas a proportional valve has got spring solenoids on both sides. And in Automation Studio, you can build these PID feedback systems here. So we'll see directly in the working copy how to do this. So let's say PID. We'll first take an open loop system. In a lot of syllabuses, we have seen PID tuning experiment, and typically these experiments are conducted using either LabVIEW or Simulink. But these systems are only simulating the mathematical controller section. You are giving a step wave input and you're observing the output for different settings of P, I, and D. But in real life, it is not only the controller which is operating. 1 minute, let me just size this. In real life, when I'm operating a system, there's a pump flow, there is an opposing force, there's a flow curve of the valve, there is loading, there's a piston which is at a particular angle. All these conditions are there in a physical system. And if you're doing a PID tuning, it has to take into consideration all these physical parameters. And it is literally impossible to create a mathematical model with so many different types of feedbacks and calculations. But somehow I've seen Jadavpur University, they were doing a lot of work in hydraulics. And those 2 or 3 doctors there, they had built these few systems for a balancing hydraulic table and another one for a walking hexapod robo. And in this, they did a lot of feed forward and feedback control systems, which they built mathematically in LabVIEW as well as Simulink. But half that work, more than not half, I could say 90% of the work is avoided because Automation Studio takes into consideration the physics of the rest of the system. Now, in an open loop system, I have taken a joystick and I've attached it straight to the solenoid valve here. So when I operate this valve, you can see the piston operating. But what is happening is when I move my joystick to the left, see the piston is running in one direction. It is not staying stable. I have to play around with my piston to keep it steady at a particular position. And this is not the behavior of a good system here. If you see the input versus output, there's a huge difference between the set point as well as the end actuator. And that is the reason we have to build feedback control systems. So we'll take a feedback system which uses a PID controller. Now in PID, we typically teach students, whoever is doing PID control, either by Ziegler-Nichols method or we are doing manual tuning practices, etc. That can be actually done on this particular circuit. Now in this case, what we have done is, instead of a joystick, we've taken a step wave input like this, so that we can take accurate plots. Okay. And we are plotting the piston output position also in this plotter. So in this circuit, the piston position, these pistons have what is known as sensors mounted on them. If you see here, we have position sensor, speed sensor, force sensors. These are feedbacks I can take in my circuit. So I take a position sensor feedback. I give it to the controller. This is a PID controller. And the graph signal is also given to the controller. The controller will calculate the error between the two signals and give the correcting signal to my proportional valve. So I simulate this circuit So tuning practices initially say that keep the proportional gain high, let's say 8 integral 0 derivative 0, and achieve a condition of what is known as ultimate oscillations. So you can see this input versus output, there are oscillations appearing here. After that, what you do is cut the proportional to approximately half the value, let's say 3.5. Integral, we introduce a little integral. Derivative usually is mostly 0 or maybe 0.02 or something like that. And you can see the input versus output. This is very good. What is a PID tuning between the set point and the actual actuator behavior. Okay, so you can play around with this PID values. Now, what cannot happen in MATLAB Simulink and what happens in the physical system? Let's say I set proportional back to 8, integral 0, derivative 0. I've got my oscillations again. Okay. But now, if I go to my pump and I change my pump displacement, you can see a lot of oscillations have disappeared. But there's an integral graph still to be compensated for. So these are conditions which depend on the dynamics of the physical system. Okay, so if these are not taken into consideration, your PID tuning in the real world is going to go for a toss. So it can't just be a pure mathematical controller simulation. The physics of the rest of the system has to be taken into consideration. And based on these, even the industry, for example, if you see Eaton has manufactured something known as the Access Pro valve. So they have a small controller PCB mounted on the valve itself. Okay, this is what the valve looks like. Now, if you see these 3 inputs here, the PID online settings can be inputted into this particular. There's a PCB inside this particular box here. So these valves are PID based controller valves, and you can actually tune these. So this is an industry, what do you say? Industry component, which is a PID based component. Okay, so these are available. It's not just theory, they are being used really widely in the real world. So that was proportional. Then coming to 2D and 3D, Automation Studio has basic 2D drawing functions, not as powerful as AutoCAD and all, but you can build virtual systems. For example, on the left, there's a excavator arm. There are 3 arms, and between these 3 arms, we have created certain joints, and those joints have been linked to the cylinder movements here. So such type of what is it? 2D animations you can build, virtual animations. So this is possible. Then we also have 3D. Now, obviously, our 3D modeler is not as powerful as any of these SolidWorks, etc., because the intention of Automation Studio is not 3D modeling and assembly. But we have a Boolean-based modeler. We can import parts from other 3D packages as STL, IGS, any of these formats. You can assemble them in Automation Studio, and you can link them to these actuators here. Now, these are 2 parts imported from another software, and a joint is created and operated by an actual piston movement here. So this is possible. So this could be like a few colleges in Pune. They are trying to create digital twins by using this 3D, what do you say, function available here. Now, for example, let's see a steering mechanism in 3D. Yeah. This is a 3D mechanism with mechanism manager as well as a Eaton steering block, all working together. So we have 3D functionality. Now coming to, that was 3D, PLCs. Okay, now this is the entering the area of mechatronics. Automation has Allen Bradley, Siemens, IC, ELSYS, PLC libraries. Okay, and yeah, someone raised a hand. 1 minute. Yes, sir.
Hello, sir.
Yeah.
Yeah, this is Anirban, sir.
Yes, sir. Hi.
Yeah, actually, we wanted to just on the proportional control valves what you have discussed. So this like you are doing in the simulation, like now I think you are going to PLC. Like how I wanted to know how to like control like actual controller with the integration with the actual controller, because this is only on simulation, right? So how to connect the actual controllers with this software. So is it possible, or uh, those things like in closed loop control also will get the feedback from the pressure sensors or the displacement
Correct.
sensor,
Yeah.
and according to that PID will move. Okay, so actual
Yeah, but just to answer
yeah.
your question in short, very quickly. See now, for example, I'll give you an example of see Automation Studio. Automation Studio has a library for block diagrams like this. Okay.
Okay.
So if you see on the left hand side, we have a block diagram library.
Yeah.
Okay. So at the initial stage, you can use this to create the control section part of it. Number one, in Automation Studio itself. Then the second option is now this can directly interface to your control circuit. I mean your hydraulic. This you can take the signals from any of the signals. Automation Studio has something known as a variable manager. If you see in the background, the simulation engine has all the parameters available here. All these can be used for feedback, feed forward, etc. Okay. So these are variables. They can be taken into this mathematical control system. They can be outputted back to the hydraulic system. I didn't show that because we are running out of time, but yeah, now this is the block diagram. This is one option, building it directly in the simulation. Now, second option is you want to do a co-simulation. Now, co-simulation, there are two options available. One is the OPC connectivity, which I'll be showing you a little later. I'm covering that in 10-15 minutes. So in OPC, you can communicate with external hardware as well as external software. And how to do that, I'll be showing you a live example. Okay. So, but that the limitation in that system is it's got a communication speed of 10 milliseconds. If you look at that, okay, 10 milliseconds is the throughput time. And if you actually buy a real powerful OPC based processor board, you could come down to 1 millisecond of sampling rate. That is second option. That is hardware interface. Third one is if you want to work at API level. Serious users in the industry, they have, a lot of them have bought the Automation Studio API, especially in a defense organization in Pune. So they have the API and they're doing a core simulation with Simulation X or with Simulink. Then they take that Simulink model and they generate the target code and burn it actually on a DSP board, which will actually do the control in the real world. So the simulation section is entirely validated first in a software like Automation Studio with a simulated control system. If you want actually interface, you could work through the OPC channel or use a API. After this is validated, then you can actually try to generate a code from this control system. Automation Studio does not allow code generation of this block diagram. You may have to rebuild it in Simulink or LabVIEW. Now, Jadavpur University, what they do is the doctors there are familiar with Simulink. So they are building the control system and the entire simulation in Simulink first. They bought Automation Studio. Then what they do is, as far as hardware is concerned, they don't have a Simulink based DSP board. They have a LabVIEW controller board hardware. So the entire system, they again redo it in LabVIEW. And that is directly connected to their DSP box they have, which is connected to the hydraulic system from where the sensing is happening front and reverse directions. So there are multiple methods.
So
So
directly it is difficult from
directly, if you
interface.
are satisfied with 10 and 1 milliseconds of this thing,
This
we can
delay
do a
will be
direct
there.
connection.
It is delay will be there, right? Yeah.
Yeah, because we've done a OPC connectivity with MATLAB. There is a step digitization of the signals at 10 milliseconds.
Okay.
If you
And
want
one
to work
small,
at full speed, yeah.
yeah, one small more question. Like this, you have done this in PID here. So can we, like,
Yeah.
suppose we have to change any other algorithm, control algorithm? So is it possible to introduce any
Yeah,
other?
you can build your entire. This is made, sir. This is built.
Okay.
This is not a ready-made block.
Okay.
These are components from the library. You can build any type of this mathematical circuit you want. We have a lot of complicated examples of these also. We can mail
Okay.
them to you, sir.
Okay. Thank you. Thank you.
Okay. Yeah. Okay. We were coming to PLC. Yeah. So in PLC, Allen Bradley Siemens IC. So building up PLC is very easy. I've built a small scratch part of the circuit here. Okay. And we teach students starting with implementation of AND gates, OR gates, etc. So you build the electrical section of the input output cards. You pull in the the contactors, output energize contacts here. Okay, you do this and you build your PLC circuit. So I've created these circuits. Now, for example, here on the PLC input card, there are two sensor switches, S1, S2. Then there's a ladder logic, and on the PLC output card, there is a solenoid coil which is linked to the valve here. If I simulate this, you can a PLC is directly operating an electro-pneumatic circuit, and obviously in the background the fluid power engine is still active, so I can reduce the compressor displacement. It will react accordingly here. So this is one PLC experiment. Then okay, very fast. We are running out of time. I have to show a few other things. For people doing PLCs and mechatronics, there are differences in the way Allen Bradley works, Siemens works, etc. Now, in timers and counters, basically, if you see in Allen Bradley, there's a T on delay timer, and these delay timers have something known as a EN and DN bit. So when the timer is triggered, the EN is high for the specified time. After 10 seconds, then the DN will come on, EN will go off. So this is how a T on delay timer of Allen Bradley works. If you see here, I've triggered the timer. After 10 seconds, EN goes off, DN comes on. Okay, so these are how these timers work in Allen Bradley. So even the symbols are very different because there's a lot of confusion in textbooks. Because in textbooks, they're following a particular type of terminology. We don't know whether it's Allen Bradley, Siemens, what. Okay, then at a comparison, if you see how a Siemens timer works, a Siemens timer looks totally different. It has got a set reset option here. You see here, T on delay timer, it doesn't have any EN, DA, nothing available here. If I simulate this, output is low. At the end of the count, output will become high. So the behaviors are different. So the ladder logic which you build changes depending on what type of a timer or a counter you're using in Siemens and in Allen Bradley. So that is something you have to take care of. The logics will change. Then we have a lot of circuits. I cannot show all of them, but let's say a circuit of a traffic light. In mechatronics, we have practicals which are all based on timers and counters. So a traffic light is 3 timers working in sequence. Washing machine is 3 timers working in sequence. Starting our 3-phase motor is 3 timers working in sequence. So here we trigger this circuit here. The first timer comes on for 10 seconds. So the red and green lights come on. After 10 seconds, the yellow will blink for 3 seconds, then reverse, and the entire thing will go back in a loop. So here there is no hydraulics, pneumatics, nothing. We are using the HMI library of Automation Studio and connecting it to the PLC ladder logic here. So this is a circuit of a traffic light. You can build an animation for, let's say, a washing machine. There are certain few things I'm going to show little after this. I'm trying to hurry it up, which are very important. That is SFC and OPC connectivity. Now, this is a washing machine animation, which I have built from scratch. 3 timers working in a sequence. The first water is pumping in. Then after 10 seconds, it is rotating and the heater is on. And after 10 seconds, water will drain out. So you can build such type of virtual systems. People have built very complex virtual systems also. So this is a washing machine. A little bit, we don't have time. Anyway, then coming to real illustrated PLCs. Now, this is a new section they put in Automation Studio in the new version in the last 6 months and 1 year, and that is illustrated PLCs. Now, in this, there are around 30 to 40 PLC models from different manufacturers like Siemens, Omron, these companies, and they are by model number. For example, this is Siemens Simatic S7 1200 series. And when you buy a PLC in the market, there's a wiring diagram which comes with it. It is not just the ladder. There is a lot of external wiring required on this PLC. And typically this is never taught unless it is a project, a student doing a particular project. For example, all the M's are supposed to be shorted to each other. Then for the outputs to go high, you have to do the plus minus 24 volt DC connections. There's a particular wiring sequence. And then there is a ladder logic which operates this particular PLC inside. So this external wiring, depending on what type of sensors you're using, 3-wire, 2-wire, you can actually create the wiring diagram. So this becomes very handy. So I'll show you something which is created for, let's say, Allen Bradley Compact Logic's PLC. The entire circuit has been created. So you can see the wiring as well as the PLC simulation operating a electro-pneumatic circuit here. Yeah. So if I start this, what happened? 1 minute. Start. Where is the power? Okay, something is gone wrong. Anyway, what I'm saying is this is the real life depiction of this PLC. This is the illustrated PLC inside Automation Studio. So you wire all this, and if you simulate, you can actually simulate this with the ladder inside. I'll just open up another circuit. 1 minute. This one is not working. 1 minute. Yeah. No, something has gone wrong. Anyway, these are illustrated PLCs. These can be simulated. Then SFC. SFC is important because this is the major market share of PLC programming. If you see, is SFC today. SFC and structured text. So if you see SFC and ST together are a bigger chunk of PLC programming compared to the ladder programming format. And if you see SFCs are based, SFC is more of a generic PLC programming language. It is not typical to a particular PLC. Most of the components used in SFC are more of a generic open sort of a programming language. And it is a sequential method of programming. So in SFC, I'll just show you circuits. So today, any PLC in the market can be programmed by using the SFC programming structure. So here, if you see, this is what a SFC looks like. I'll explain this to you in very short. So on the piston, there are two sensors S1 and S2. Whereas on the SFC side, there are basic 4 steps. It says that if solenoid 2 is active, activate sensor 1. If solenoid 1 is active, activate sensor 2. Sorry, sorry. If sensor 2 is active, activate solenoid. If sensor 1 is active, operate solenoid 1. So in simple 4 steps, you get a cylinder reciprocating circuit. Whereas the same thing in ladder becomes quite complex. There are too many rungs and too much of things to take care of. So this. And SFC also has a particular section which is known as structured text. Okay. And structured text is what the SFC program actually creates in the background. So you can either program by using structured text. So the same program, what we saw previously, can be done in 2 lines of code here. Exactly the same function, what we saw previously in 2 lines of code. Solenoid 1, if sensor 1, solenoid 2, if sensor 2. Whereas you can imagine trying to create this same logic in a ladder program. It's quite complex there. So SFC is the future of PLC programming. Then hardware interface. Okay. Okay, Automation Studio, we provide this IO box. Okay. And this is the OPC based IO box. We have sold more than around 40 boxes to a lot of colleges across India. Okay, but these are not high speed because a software is communicating through OPC software to a particular hardware and then again to another external hardware. It's not too much of a high speed, but it suffices for experiments of electro hydraulic, electro-pneumatic, PLC control, etc. So in Automation Studio, you can build the ladder logic, electrical logic, and through this box, we can directly connect 24-volt signals to your electro-pneumatic, electro-hydraulic kits on the external world. Vice versa, in Automation Studio, you can build the hydraulic pneumatic circuits and you can control it using an external PLC. Both way communication possible as long as it's 24 volts, signals passing up and down. So a lot of colleges are using these instead of PLCs. Then screen is visible. Now, for example, this is CET Bhuneshwar. You can see here they have a electro pneumatic kit here, hydraulic kit, and this is the IO box. So they are users of it. There are a lot of colleges across India where we have sold this. So this becomes quite interesting. Students have done practicals like this. So simple pneumatic based practicals where the IO box is used and online the PLC and Automation Studio is connected to this particular project here. So this is also available. Then, okay. Coming to OPC, we have around 10-15 minutes left. And in that, I want to cover OPC and a few projects in real life. Now, why am I giving so much stress on OPC is that because OPC today has become the backbone between in automation industry. So entire plants are using fiber optic OPC backbones to communicate between hardware to hardware, hardware to SCADA, SCADA to PLCs, DSP boards. Then also things like software. You can do software to software communication also. And certain colleges a few years back, for example, Cummins College, Pune had introduced OPC as a part of their curriculum. But then because of the non-importance of the automation industry, it diluted from the syllabus. But I know that a lot of y'all are doctorate level, MIT, NIT, IIT levels and autonomous colleges. You can introduce such, future trends, not future, this is already being used today in the industry. So OPC, actually, it's a standard of data exchange. Initially, it was known as OLE for process control. Later on, it was renamed as Open Platform Communication. Okay. Now, the old type of OPC was known as OPC Classic or DA, and the new type of OPC is known as UA. What can happen in OPC? I'll just explain that. 1 minute. Yeah. So in OPC, basically, where is my? I have so many files. Yeah, this is the right PPT. So in OPC, on a Ethernet cable, there's a OPC server residing somewhere on that network. Okay, you can connect OPC via Ethernet cables. Then that acts as a data exchange server, and that can connect to even things like Microsoft Access databases. You can log data there. You can communicate PLCs. You can communicate any of the processor boards from any of these Dynalog, Siemens, Beckhoff, Schneider. All these are communicatable through OPC servers, and all of them today support OPC to the extent that even large size projects like the Hadron Collider in Geneva, the 27-kilometer Large Hadron Particle Collider, the entire data polling of the cooling section is done by using OPC. So there are 200 data points, which is polling data around, I think, 1 hertz, and millions of points of data are being logged by using a OPC backbone. So even these people are using OPC as data logging. And you can see here 180,000 OPC tags, 1 lakh front-end devices, services or devices, you could call them FEDs. And these are used even in a large project like that. OPC servers are available from almost any processor or PLC manufacturer today. Matricon, Iconic, Siemens, Mitsubishi, all of them are providing OPC servers. Now, 1 minute. So you have a PLC that communicates to the OPC server and that communicates to the OPC client. So if you see Simulink, most of you all must be using Simulink. Simulink has a OPC toolbox. Most of you all may not be aware, but go to Simulink. Simulink, I think in Simscape. No, not in Simscape. In the basic Simulink list of modules, you'll see OPC toolbox. And it's a very simple procedure of communicating data between Simulink and Automation Studio by using that OPC connectivity. If you see in the Industry 4 model, in the practical world, in the industry, on the field level, on the floor, backbones are OPC. And even the data going to the cloud. Today, if you go to Amazon Web Services, you go to Microsoft Azure, any of these cloud services, you go and read up on them, you'll see a OPC option available there. You can create OPC channels for communicating to hardware devices. So this is there. Now coming to how does it work? On my machine, I have loaded something known as a Matricon OPC server here. Matricon, where is it? Matricon OPC server. Okay. And this is what an OPC server looks like. And in this OPC server, I've created data tags. So I've created analog 1, 2, 3 and digital 1, 2, 3, 4, 5, 6. Different types of data tags available. Okay. This is running in the background. And what I do is I go to, let's say, Automation Studio. Automation Studio. In Automation Studio, I'm opening a circuit which I've built. Let's say communication to a SCADA software. Okay, this is, no, not this. We'll not take this one. We'll take WinLog SCADA software. So I'm opening up a circuit in which there is an aircraft landing gear circuit in Automation Studio. The movements of the pistons that signal, I'm going to send it out of Automation Studio to the OPC server running in the background. And that I'll read it in a third-party software, which is a SCADA-based software. Okay, so this is the basic circuit here in Automation Studio. Okay, now in Automation Studio, I have this communication manager here. Okay, in this, if you see, there's an option of OPC DA and OPC UA available here. So I have connected Automation Studio signal to Matricon OPC simulation server, which is running in the background here. This software detects Matricon OPC server running in the background, and I've created links. So the links of these signals, these analog signals, are being sent to the OPC server in the background. So I'll minimize this now. Then what I'll do is I have a SCADA software, third-party SCADA software by the name of Winlog. What is it got? Winlog, yeah. Winlog Project Manager, in which I have built certain dials and gauges. Now here also I can set my OPC connectivity here. I say run this particular template here. This is a third-party SCADA software. Okay. And now I'll simulate Automation Studio. Where is the circuit gone? I'm trying to fit everything on screen. Just give me a moment. Yeah. I simulate this. And I open my aircraft landing gear carriage. So you can see the hydraulic circuit is simulating. The piston position signal is being sent out to the Matricon OPC server running in the background. Okay. And that is being read by a third-party SCADA software here. I retract the landing gear. So this is communication between two totally different software, both supporting OPC connectivity. So this was one example. I'll show you another example. Another circuit in which I have interfaced Automation Studio to a third-party 3D automation, sort of a factory 3D type of a software known as Factory IO. Okay, and then these are buttons here. And in automation on my laptop, I've got, where is it gone? Where is Factory? Where is Factory IO? Yeah. So I have this Factory IO software. This is a demo version. Okay. Now this is a 3D software, and I'm going to open a particular 3D simple model here. Okay. So in this software, if I go to the drivers option here, you'll see this also supports OPC client here. And these are the data tags. And this is linked to the Matricon simulation server in the background. You can see the tags available in this Matricon OPC server, analog 1, 2, 3, 4 here, are seen here inside the factory software here, analog 1, 2, 3. Okay. And now if I simulate Automation Studio, I can operate, 1 minute. I can operate this between two software here. So this is using the OPC connectivity. Now the same OPC connectivity can also interface to real hardware. So tomorrow, if you have a processor board, which is almost all of them, I could say 99.9% all of them support OPC today. So even through a TCP/IP cable, you can plug it into, for example, Siemens S7 1500 series PLC is now a higher version. Let me see online. For example, Siemens 1500 PLC. If you see, this is a Siemens S7 1500 series PLC. Now, this is not a normal PLC. This comes into the processor category. And this has an embedded OPC server inside the hardware. So what I mean is that if you plug in a TCP/IP cable into this 1500 series PLC in the Ethernet port and connect it to my laptop, I will be able to read the data tags directly into the hardware. So there was one question by Dr. Sir sometime back. Can I communicate? Yes, through OPC connectivity, I can communicate like this. The data speeds will be, however, between 1 millisecond to 10 millisecond, this thing. So this is available, 1500 series. So that is the OPC backbone. Then, 1 minute, where is that going? Let me shut this down. Anything else in OPC? Okay. For those people who are experimenting with IIoT and data hubs, etc., we do not have too much expertise in developing this, but I'll show you the way it could be done. Now, instead of using, Raspberry Pi and using those that type of a channel is very, very primitive now. In the industry today, there are direct gateways. So there are Siemens gateways. There are a lot of electronic DSP manufacturers providing gateways which directly connect to Azure, AWS, etc., either through MQTT clients or it could be REST clients. And you even have software. For example, Cogent is a company, one of a type of a company which supports OPC, DA, UA, you can see here, as well as it can communicate to the cloud through, if you create those channels, you have MQTT client, you have MQTT brokers here. These are available here. Okay. So we have software like this, which can communicate to cloud services. And at the back end, a software like Automation Studio can work through this data hub. Okay. Now, for example, okay, this is what I've done is a data hub like this. I'm logging data from Automation Studio. So Automation Studio OPC server is talking to this data hub here. You can see this piston extraction and retraction here in this circuit here. This is happening here, and that data is being logged into OPC and a IoT gateway hub here. The point being, we are talking to a hub. This is a gateway to the cloud. So you can communicate through such hubs and such type of gateways via the OPC backbone. So this is possible here. And today's forum is hydraulics, pneumatics, and automation. So this becomes a very big. This plays a lot of importance in automation industry. Now, towards the end, in the last 5 minutes, certain student and other projects I want to show you before we end the session. I think we already overshot our time. Just 5 minutes. Now, for example, let's say one of the projects was for a hydraulic forklift. This was done by a third-year undergraduate student. And even a paper was published on this particular forklift because it had a lot of design aspects in this particular project. So this student used a lot of industry catalog components and built the entire thing from scratch in Automation Studio. So a forklift which has got a power steering section as well as a lifting and a tilt section here. Now the design section, I'll tell you, this particular dotted block is a Eaton steering block, a steering manifold block. This was designed from scratch. This has got a servo motor mounted here and a metering device which acts as a feedback angular device here, giving the feedback. Then a flow divider was used. A flow divider is used to split the flow, 70% going to the lifting section, 30% of the flow coming to the power steering section. Then on the right hand side, these two valves are from the Danfoss PVG 32 valve group, known as proportional valve group PVG concept. And this is what it looks like. And these parameters are fed into these valves, and this block was created. So one valve was operating the tilt cylinder. This tilt cylinder was facing different types of forces because the intention was to pick up a load of 4,000 kgs. So when when the two forks go under the load, either of the cylinder could hit the load before the other cylinder hits. So erratic loading conditions were to be considered. So if you see between the two pistons, there were two different loading conditions. And then we had a static lifting ram here. So a lot of other conditions like steering from left to right shouldn't be more than 3 seconds, etc., etc. A lot of design conditions were there. So we have the power steering section on the left hand side here. Okay. And then on the right hand side, we have the tilt section here. Okay, this is a proportional valve, but a mechanical proportional valve, not an electric operated here. And then we have the lifting section here. So this was one student project, third year undergraduate UG mechanical department. Then we have things like a PLC based cotton baling machine. So the student project was that this machine was electrically operated with buttons. Cotton had to be pressed. So this had to be an automated PLC based operation. And in this, one condition was that these three pistons had a plate welded on them, and they acted as a compressive mechanism. So a mechanism manager, which we saw, this was used here. This came in handy here. Okay, so this is a cotton baling machine. You simulate this. So the sequence of operation. Now, even these three pistons, they go to 50% 3 times, and in the last stroke, they go 100%. It is like pressing cotton with your hand. You first go slow and then press it fully. So that type of a design was created here. This was cotton baling machine. Then last just 2 or 3, then I'll end this. Cotton mill landing gear, GCOE, turn hitching, batching system, conveyor sorting. Okay. One defense project I want to show you. It is interesting, so you'll know what type of work happens there. So this one, I cannot give the name of the organization, but the project was that it was a hydraulic system. When an aircraft misses the runway critical point, a net at the end of the runway comes up. Otherwise, it is on the ground. So a sensor signal goes and this net is picked up and it grabs the entire 60-70 tons of the aircraft traveling at maybe 200 miles per hour or something. So this was a very big design consideration here. So this was one of the projects, and part of it was test bedded in Automation Studio. So how many people are online? So in this defense project, we did a small benchmark. They didn't give us the entire circuit. So now in this, if you see, being a defense and an aerospace, aeronautical requirement, everything was double backed up. So if you see the pump, there's a double pump assembly. Not only that, if power failed, there was a hand pump you could use with your hand to pump the fluid. Now, if the electrical power failed, okay, and the national grid came down in case of a war, there were 3 accumulators which were charged, and these accumulators had enough of charge to capture 3 aircraft one after the other without electrical power supply. And then these are the pistons here designed to capture such a high load of the aircraft. And the mechanism manager to simulate the actual mechanism when the aircraft rams into this particular net. So I simulate the circuit. Then once this is done, I switch on motor 1, motor 2. there are things like pressure switches to maintain the accumulator pressure. Then I have raised the net. The net has been raised. Now there are design conditions. For example, when the net is on the ground, the weight of the net on the pistons is 0. But as it rises up, 900 kgs of that net load first comes on the piston rods and then the aircraft slamming into it. So all the design considerations were taken into consideration. Now I want to ram the aircraft into this particular net. So I trigger a graph, and at one point you'll see the mechanism slightly buckling but still holding there. I'll do this again. I'll trigger the graph again. You can see, you can watch the mechanism manager. So it depends. There's a lot of projects. It could be bridge laying machines. It could be missile launching system on trucks. Different applications depending on what the requirement is. So this is that. And before I end my demonstration today, College of Engineering Pune is one of the very big users of Automation Studio, and they had a few projects. They had 2 published papers, and not only the hydraulic pneumatic section, they went as far as to actually do a IoT based project by using Automation Studio. So one batch of MTech Mechatronics batch, they used the IO box of Automation Studio and they did a conveyor sorting system here. So a laptop had Automation Studio PLC running, and through the IO box, they created this conveyor sorting system here. Okay, this was one project. Then stamping, a simple project by using the IO box. This was another project. But the main was the IoT based projects. Okay. Now, PLC based fluid power system to IoT system. I'll just show you the main pages. What happened? Okay, so this was the hardware they had built. It was a clip making machine. A piece of metal is taken and it is bent into 2 sections, create a paper clip. And this data from sensors was put into the IO boxes, and this signal was detected into Automation Studio. So the intention was catching the events of these sensors, how many clips were made, how many times these pistons operated, etc. Okay, so obviously the rest of the report is there, the PLC used in the background. And then using ThinkSpeak and Raspberry Pi and Python, not Raspberry, sorry, Python, and using the Matricon OPC server, they communicated this data to ThinkSpeak Cloud. ThinkSpeak is a free student version of cloud. So they did that. They did a little bit of Python scripting here. Python also has an OPC toolbox with it. So even they support OPC. And they build an Android application. Yeah, this is the setup here. Automation Studio, IO box, the actual system. Okay. And this is the Android application, which was again interface to ThinkSpeak Cloud. So here you could start the system and you could also capture the amount of times the pistons operated, etc. Yeah, number of cycles were being captured here. So this was one project. The second project was even more interesting. Is a published paper. They already had a PLC simulator in their college. This was a 4-floor PLC simulator operated by a Mitsubishi PLC. So what was done was, through the PLC, they pulled out wires without disturbing the existing wiring of the PLC. They pulled out signals from certain points of the PLC input-output cards here in parallel. And that signal was taken through the OPC server into Automation Studio and the Android application. So Then this events were captured here. Door open count without interrupt. Okay, there are different types of data they were capturing. Empty trips, number of loaded trips, number of times the door opened. So all this data was being captured here. So this is just the brief paper. The entire project report is around 30-40 pages. So this was another project.